Good afternoon, everybody, and thanks for coming. I know it's Saturday, and I'm between lunch. I'll try and make it quick and entertaining. I work out of the San Francisco office here. I lead the customer deep learning stuff at AWS. I am pretty passionate about both deep learning and serverless computing. So I thought I'd give a talk at the intersection of both these topics. My background has been distributed systems and machine learning. Prior to this, I actually co-founded a company in the computer vision neuroscience space. I've worked at Zynga, EMC, pretty diverse background in terms of companies I've worked for. So let's take a look at. Actually, I'd love to know how many people are interested with the serverless part of the talk. Pretty much all. How about the machine learning, deep learning side of things? Oh, okay, that's great. Perfect. So quickly, if we think about what's the pipeline that we go through, thinking about creating our model and deployment, right? So we go from data, we process it. The data is never clean, right? So we need to get it into a format where it is. It's actually feedable to the machine learning algorithm or the process. So typically what we do is, in case of supervised learning, where we have data and label pairs, right? And unsupervised learning is where we just have data and we're trying to find trends in the data. Now, with supervised learning, what we would do is we'll always divide the data into a training and validation and test set. The idea is, more often than not, we're trying to create a generalized model. So we need to know, hey, with the data that we have, is the model generic enough that it is going to run in the wild? And then we do feature extraction, we do model generation, we do the loop, we test, we look at what the metrics are. And sometimes the hardest part is actually defining the metrics for your model evaluation. So we'll start with, we'll try and just be serverless all this time and see what we can do with the current tool set that we have. We put the data into S3, now what, right? So AWS Glue, we can categorize, clean, ETL the data. We also have Athena, where you can run standard SQL queries. But you're kind of assuming already the data is sort of processed or in some loose structural format for you to do that. But the real game is we have dirty data. How do we actually put it into a semi-structure or an actual structure where we can process? So about a year and a half ago, I built this serverless Map Reduce paradigm that I thought it'd be appropriate given there are a lot of big data lovers here. So the idea is, can we just run MapReduce, a well-known paradigm, just completely serverless? That is, no provisioning of resources other than, or an actual server, right? So just using S3 and Lambda, can we set this up? Now, I probably should have had the architecture first, but I'm just going to go through quick. Okay. So what we have is, let's say your data is stored in S3. Now you can actually specify with a driver function. You write the mapper function, you write the reducer function, and the driver basically creates. This is a script that lives, either it can be a Lambda function or it can live on your computer. This is just initiating the creation and provisioning of the functions. So you basically map you can map the files on S3, and your mapper, it can provision a bunch of mappers, then the count can be proportional to the number of files you want to process, and it runs, and then you have, it actually writes it to S3. But now, here's the part, right? Like, we need to do the reduce step after we do map. So in order to make that serverless, we have a coordinator Lambda function that basically gets invoked every time the mapper writes an output. So that's because Lambda is stateless, we use S3 as a mechanism to maintain state and where we are in the process. So that does the magic, and then recursively reduces based on the outputs that we get, and then finally we get the output. I'll walk through this. Actually, there you go. So execute the driver. We then enter the map phase, where we provision the mappers. They write the map output to S3. The coordinator gets invoked. It checks, hey, have all the mappers finished? It goes recursively. And then once the mappers are finished, it does the reduce steps. Now, we don't need to wait for all the mappers to finish, but this is just an implementation where the idea was to show that we can actually do this serverless. And then the reducer goes recursively until a single output file gets created. This project is actually on GitHub, and I'll actually go through a use case. We'll run it live. I have a video just in case it doesn't work. So let's just say the demo gods. So here's what happens. So how many of you are familiar with VPC flow logs or flow logs? Just one. Anyway, so what happens is a lot of times people provision their own private networks. So it'll be generic here. And now you want to know what's the traffic between each of the interfaces. And so the idea is you can log every packet that comes in your network, and then you can look at, okay, what pairs and what's the traffic in and out of every Ethernet interface. Now, that's sort of what VPC flow logs is. And surprisingly, you can create more data than existing data because each packet is logged. So very quickly, your data set grows at a more than exponential pace, even if that's possible. So what we do is we have a bunch of files. So in this case, I have, I think, 4,200 files. Each file is essentially log. Let me show the. Thought I had a file here. Anyways, so as you can see, the number of keys, we have about 4,241 files, and the total file size, total data set size is 4.2, actually 424 gigs. So massive data set that we're processing. And what we do is we provision the Lambda function, 3 Lambda functions that I called out. And the mapper logic is fairly simple. As you can see, it gets the data from S3. It does the split. Each line is a new line. It's split by a new line. And you get the interface ID, you get the status, and you get the bytes. And we're just aggregating the bytes. So if it's in the SQL equivalent of this is basically aggregate according to the Ethernet ID. That would be the SQL equivalent of what we are running here. And and we have the reducer. So it basically creates 3 Lambda functions. And I've just run it in a pipe request response mode so that I can calculate these stats on my machine, but everything else is happening remote. So as you can see, we get the mapper outputs, and the first column is the number of files, second column is the number of lines, third column is the time it took for that mapper to basically run. And we'll wait. I think that's almost done. We can go into S3. I might have not changed the name, actually. I should have changed the name for Yeah, I mean, this was the one that I ran earlier just to make sure it works, right? So 7:49 a.m., that's when the state was created. 7:51:24, that's 2 minutes and 6 seconds. We actually have the task finish in that time. So, and it just collects the stats here. As you can see, we processed 3.54 billion lines, and the cost, more importantly here. So we ran in 2 minutes, right? 420 gigs of data processed in 2 minutes, and the total cost was 53 cents. Like, so for tasks that are massively parallelizable, where the map task is the bottleneck, this paradigm seems to work really well. So this is a summary of what we saw. We have 3.5 billion lines of code. Lines that we processed, 4,200 files, and roughly each of them are 100 megs each file, so which makes it around 420 gigs. Now, what's interesting is MapReduce is a very generic parallel programming paradigm, right? So even though we've sort of moved to better, paradigms, so to speak, it's still pretty powerful, where you can express a lot of algorithms in MapReduce. And because it's inherently parallelizable, it's pretty cool that we can go build a lot of things. And what can we build? Like a lot of different linear algorithms and some nonlinear algorithms as well on top of this framework. So as an attempt, it's like, hey, let's actually run some k-means clustering and see if k-means clustering is possible using this. So it works pretty well. So the algorithm is pretty straightforward, where if people don't know what k-means clustering is, we have a bunch of data. We're trying to find, okay, if we say 5 clusters, what data points go into which clusters. So we randomly initialized the centroids of the cluster, and for example, what I ran, I'll show you some graphs later, is running where news stories originate. So there's a global information or news data set which gives you, hey, the news story happened in Tokyo, news story came out of San Francisco, and they give you the geo coordinates. So the idea here would be, hey, can we actually find where the gravity of the news is for a given day? So let's say we want to identify 10 centers in the world. We would initialize it with 10 centroids. And here the centroids would be the coordinate system that's the lat long, right? So we'll pick random lat longs, which valid random lat longs. And then what we do is we take a point, we see how close it is, and then we update the centroid, and so on. Now, you repeat this until your centroids converge. What that means is when the centroids stop moving, that means that you've essentially converged. There's no further movement. So one of the visualization here is, so this is just on, I didn't have time to run it in the morning today, so this is year-old data, but that's what we see as that's the center of news stories. So if I pick 5 stories, so you can see it sort of moves, day to day. And I'm pretty sure that we'll have more red dots these days in the US. So how is this useful? One of the things you can think of with k-means clustering is log clustering. So what are the let's say you have a bunch of servers, which servers have the most error rate, or if you have Apache or Nginx logs, you can kind of see what's buggy. So this is pretty useful where you can just have an entire pipeline which is serverless, right? Like, and the cool thing here is, unlike your MapReduce clusters where you're limited by the number of operators, or rather number of jobs you can run on them, here you're not limited, right? So as long as, let's say your Lambda function limit is 10,000, that means you can run 10,000 functions concurrently. So you don't clash with anybody. You can keep running your programs in isolation, and there isn't an overhead in terms of, hey, I need to go to IT to get my machines provisioned and all of that. So pretty flexible. So now let's, I'll sort of move on the deep learning side of things. So as we kind of think about three distinct phases, right? So data processing, training, and inference or prediction, right? We went to the data processing side of things. We now looked at how can we train things serverless. There are actually mechanisms where you can actually load and train on a Lambda function, but we are currently limited by the whole notion of having the time aspect, right? Like currently we have a 5-minute timeout on a Lambda function. So you can sort of chain Lambda functions and so on, but when you're doing real complicated modeling, it's sort of like you need the GPUs, you need the horsepower to train on large data sets. So we're not quite there in terms of training neural networks on Lambda, but certainly doable. So quick poll, where do you think we spend the most time in these three phases? Like, if I say, how many people think that you spend a lot of time on modeling rather than data processing?
Is this compute time or real time?
Real time.
Oh, okay.
Yeah.
Pre-processing.
Yeah, I'm glad people agree. Yeah, that's true. we tend to spend a lot of time on data processing. The model, kind of soon follows, and on the writing a prediction and inference side is pretty trivial. But actually, the fun part is, like, what would you say the typical cost, spend on inference versus training? Like, anybody wants to give a split? How many people think you spend 50% of the time on inference and 50% time on training? No? 70% on inference and 30% on training? No? Higher or lower? Higher? Okay. Yeah, so that's true. So practically what we have seen is it's typically upwards of 95% of the cost spent on inference. So this is talking to various teams outside and within Amazon as well. This is what we observe. Is a lot of the time is spent on inference. In terms of a lot of the cost is significantly larger on the inference side. So which is why I wanted to spend time focusing on inference and prediction part aside. What I've done is I've actually open sourced 2 of these repos. I just didn't have time to make the third one, and somebody had already done it. So, so MXNet, Apache MXNet, there's a repo where you can have pre-trained models deploy, and rest of the logic is taken care by the framework. Same with Keras, so you can have trained models, and then even TensorFlow on Lambda is available there. So I'll walk through quickly how to do this. How many of you here like notebooks? Right, a fair bit, right? Like, so I think it's like it's kind of annoying where you have to use too many different tools and move around. So I'm like, hey, I'm just going to write a Lambda function and edit and put it just in Jupyter, right? Like I just want to be able to modify, deploy my Lambda functions right here. So I actually wrote a notebook where you can see that it's a little hack to say, hey, don't execute because you're probably not going to link all the libraries that are needed. But the idea is Lambda function has a limit of 50 megs. Now, so if you have a large enough model, and some of these packages are, I have like 400 kilobytes to spare with all the zips, so you can it's very difficult to add those models there. So the idea is, what can you do? So the best practice would be to store the model in S3 and download the model because the bandwidth to S3 is pretty darn good. I think I forget the numbers now, but I've been able to get 35, sometimes 70 Mbps. And because this is all in the AWS environment, you don't pay for the data transfer, so works out pretty well and cheap. I'm just using the HTTP link here just to be generic, but you would want to use the Boto client if you're using Python to download. But the model is downloaded outside of the Lambda context handler, and the idea here is that you're not downloading the model on each request, right? So you get to keep the model in memory and execute subsequent requests. Don't need to download that. So this is a very simple model here. Actually, this one is a geolocation model, which is essentially given an image, it tells you where the image was taken, and we'll demo some of that. So it packages the code, uploads, creates the Lambda function. But what I've done is I've integrated it with a SAM, serverless application model, which creates an API gateway endpoint and hooks it to the Lambda function. So you have a prediction API in no time. And all you need to do is basically plug in your, make sure you have the IAM role correct, and then plug in your account ID, and plug in your bucket location, and that's it. The rest of the stuff is all automated, and you can work out. So we can just, this is a fun, so anybody knows where this is? Antarctica, yeah. It's actually a pretty remote place where there are hardly one of the most remote places, Svalbard in Norway. And actually the model is pretty cool that it can actually detect where it is. So let's actually, I'm going to try and see if it can detect where we are. I have no idea. I've not run this. No, it says it's it's Michigan, Illinois. It's sort of hard, right? Like there's no real. This could look like any other building, and unless that's actually part of the data set. But it's actually pretty good at, let's say. I think we've done enough of the bridge, so let's look at quite.
Did you want to comment out that first image?
No, I'm trying to get a different.
Back on your Jupyter notebook.
So.
3 image URL. Did you want to comment out the first one when you ran?
No, it just overwrites, right? So I mean, here's. I'll show this example. Anybody know where that is?
New York.
We'll find out. We'll know. So that is New York. It does get it right. But I mean, let's not fixate on the model here. The idea is, how can we actually run, and what is the how long does it take to actually run these models, right? Like that's the focus here. So I did some benchmarks, and I think my screen is frozen. There you go. Yeah, so the model, I deployed a ResNet 18 on using the same mechanism. It's a model that, it's a simple classification model, gives you given what's in a scene, right? Like, is that a person in the scene, or is that an author, whatever. And this is a classic ImageNet model, which is about 1,000 classes. What we see is, I mean, even at like 75 requests per second, on the left side in San Francisco, like the average was about 1.2 seconds, which is pretty decent when you think it has to go download the model, keep it in cache. It has to download the image, pass it through the model, give the inference, and get back. And on the right is a map of latency across the world. I just wanted to see how that affected. And not bad, like the worldwide latency was about 1.5 seconds. So not quite real time, but again, we all have different definitions of real time. And when you take into account the cost aspect, this works out to be a fairly cheap affair to run your even your production workloads. And similar, so what I want to do was deploy an object detector model. So let's see, given this dog, we can identify where, if this is a dog and where the dog is in the image. And the execution is because I've not executed this, so Lambda, as you're aware, there's a warm-up time, right? So the model has to be loaded. So let's see how long it takes. Probably going to take about 10 seconds, maybe. Yeah, so the model prediction time itself was about 1.15 seconds. It's faster. So, and yay, we almost got the dog. We missed a little bit of the nose, but so it's pretty close. And similar, what I've done is this is with Keras. Again, similar code where we download the model, keep it outside the context handler, given some helper functions. As far as you're concerned, you just need to override the Lambda handler to do whatever the task is and extend that, and the rest of the stuff should just stay the same. This is actually running a SqueezeNet model, which is a much smaller model than a ResNet. And I did benchmarks yesterday, and the round trip from here to Oregon at about 100 requests per second was 380 milliseconds. I do have a blog on this as well. Platform we are framework agnostic. So we're an open platform. I wanted to make sure that we have enough support to run pretty much any available deep learning framework out there on AWS Lambda. Okay, now comes, right. So things to consider, right? Like, yay, we have deployed our model, but we're always thinking about as engineers and somebody who's handling production is what's the CI/CD pipeline look for this? How do we think about that? A, where do we store the models, right? B, how do we version these models? Like, we need a model management system, so to speak, just like GitHub for models or something like that. So how do we measure the performance and latency as we kind of like release new models? Also, how do we even roll out new models? How do we know Model A is better than Model B, and so on? So one of the hardest things is what's the ground truth, right? Like how do we evaluate a model? Remember, like we kept a test site and a validation set so that we can test on the model, but hey, that was done on the data that we collected. How do you actually know that this is a viable option and what we see in the wild? And let me tell you, when you deploy the models and things in the wild, totally different. Doesn't matter how much data you collect, it doesn't always add up. So it's always good to kind of like keep in check and looking at the ground truth and have a strong model evaluation technique. So traditionally, well, we can A/B test our models, right? So A/B/N test, and essentially, as I said, like you take a lot of time to find what that metric is that defines that model A is better than model B in the real world. A/B testing, well, we need something more sophisticated, like so enter MultiArm Bandit. So A/B testing could work, but MultiArm Bandit is a more sophisticated system which can help us evaluate the model. So essentially, the idea here is, let's say you had multiple arms, and the classic example is a slot machine. Let's say you have 10 slot machines, which you're trying to understand which lever do you pull to maximize the chances that you're going to win, win from the one particular slot machine, right? So you're maximizing your outcome. There are different strategies. One of the strategy is, hey, let's choose the best model. We will run it for 70% of the time. 30% of the time, we'll allocate to other models in the system. You can do probability matching, or you can learn the distribution as you get the data. You can learn the distribution of which model works based on the context of, let's say, a personal user or somebody. Some of the challenges with MultiArm Bandit is like it basically, you will have a phase where it'll explore and then it'll just switch and serve all the traffic to one model. So there's no smooth transition, and you kind of want to hold back, and there are strategies where you can hold back and kind of see if it's still valid. What you saw valid yesterday is still valid today, and so on. Also, you're wasting resources, right? Like let's say you have 20 models, and your model is the source of how you generate revenue. Now, if you give a bad model, there's an opportunity cost associated. One of the ways to mitigate that is using a prior, so essentially weighting each of the model. Now, how does this look with what we talked about, predicting these on our Lambda talk, right? So here's the MultiArm Bandit approach. So yeah, took some time to draw that. But the idea is you have a sort of a router Lambda where you either can store a state like in S3, or in this case, like percentages of which model needs to be either the prior or the epsilon distribution, or each of the probability of the model. Or that can be sort of hard-coded here if you want in the Lambda function, so that you don't hit the S3 to fetch that one file. And then you want to make sure you're using something to collect the data. So given we're talking serverless, DynamoDB is a great tool here to collect all your metrics on the inference side. And now on the same Lambda function, you can have different versions which are pointing to different S3 models or models in S3, and you can think of this as real time, right? So you can have either using Dynamo streams, or you can have a background Lambda function that collects, modifies the percentages, the serving percentages. So you have a loop, a system that learns which model is performing better and directs the traffic accordingly. So you're not static in terms of what you saw. So this is what I highly recommend as a strategy when you deploy new models. Previously in my company, I've used this strategy, and I know a fair bit of more sophisticated pipelines do look like this. And this is one implementation that you can leverage for serverless deployment. So I know I went a little too fast. I wanted to kind of give a spectrum of all of this. So I'll pause here and I'll take questions. I'll be out even after the time. More than happy to give you guys insights into my work here. Thanks.
Thank you. That was a fascinating overview of how to do ML on Lambda. Questions?
Maybe we could keep the model inside the script, like serialize it in a JSON and put it inside the script.
No, that's the problem, right? Is the 50 meg limit on Lambda, which is why we can't, because the whole package itself is, as I said, like has 400 kilobytes to spare. Given all these wonderful shared objects and binaries that we have to put in, it just takes a lot of space. Sorry.
Is there any plan for Amazon Lambda to increase their limits?
If you kind of typically look at, we have a continuous process in the fullness of time, yes. Yeah. I mean, we've gone from, on release it was 1 minute, and then we went to 5 minutes about a couple of years ago, or last year, I forget.
So right now one of the limits is that you have to download model from S3 to your local Lambda disk. Is there a possibility, or maybe to import model directly from S3? Maybe it requires some modification, but to bypass this 500 megabytes limit.
No, what it does is it's actually not. It's actually keeping the model in memory. So it uses a temporary file mechanism. I mean, you can because the Lambda using the temp space is not. I wouldn't recommend, because the temp space itself is 500 megs, right? Whereas the memory limit is 1.5 gigs.
Yeah.
So it's better to keep it in memory than write it to disk and read it, because you don't want to pay the I/O, right, of disk reads. So it's easier to keep it in memory.
Yeah, so but you can basically read straight from S3 without using hard disk to store model.
Yeah, sure. Yeah, that's what I would do. Like if you use the name temporary file, you can use the name temporary file is a temporary file created in memory, and you can only when you flush it flushes to disk.
Okay. Thank you.
More questions? No? Then we'll let you all go to lunch.
Cool.
Thank you again.
All right, thanks guys.